Okay, let's unpack this. Imagine that everything you could possibly see out there, every star, every galaxy, stretching out billions of light years.
Yeah.
Imagine it's not just drifting apart because the universe is expanding. What if it's also being pulled, like in a specific direction, almost like some giant, unseen cosmic current dragging the whole shebang along?
Okay, I'm with you.
Well, this pretty mind-bending idea is called dark flow, and, well, it suggests the universe might be a whole lot weirder than we thought.
And what's really interesting for this deep dive is the range of sources we've got. You've pulled together quite a mix.
Way up.
There's that Emergence YouTube video, which is great for visuals, kind of gives a foundation. Yeah. But then you've also got the proceedings from a Royal Society meeting.
Right, where the top scientists are really grappling with, potential cracks in our standard model of the universe.
Exactly. Serious stuff.
And then we've got articles from NOVA, PBS, and Space.com giving that sort of journalistic take on the discoveries, the debate.
Which is crucial for context.
Totally. Then there's the wild card, a Reddit discussion, where you get those completely unconstrained, out there ideas popping up.
Always interesting to see those.
And finally, sort of bedrock for all this, an actual research paper from RAC, looking at the real data, the movement of galaxy clusters that's hinting at this dark flow thing.
Okay. So our mission then is to try and piece this cosmic puzzle together. What is dark flow exactly?
Yeah.
What observations are pushing scientists to even consider something so, radical?
And what are the big arguments about it? Is it real? Is it not?
Right, the debates. And the really tantalizing bit. If it is real, what could it be telling us about, the universe beyond what we can actually see? Maybe even beyond our current physics.
Okay, so before we dive into the flow itself, we kind of need to establish the basics. Like, how much universe can we actually see?
Good starting point.
That Emergence video did a nice job explaining the observable universe. It's like, think of it as a giant bubble around us. Anything inside that bubble, its light has had enough time since the Big Bang to travel across space and, reach our telescopes.
That's the key, isn't it? The universe is expanding, light travels fast, but not infinitely fast.
Right.
So the observable bit isn't necessarily all of existence. It's just the part we have any hope of getting information from.
And inside that bubble,
the
video mentioned, what was it, an estimated 2 trillion galaxies.
2 trillion. It's just, a staggering number.
It really is.
Yeah.
Almost impossible to wrap your head around. And it leads to that big question the video brought up. If there's this edge to what we can see, this cosmic horizon, does that mean the universe just stops out there, like hitting a wall?
It's a great analogy, the wall at the horizon, because that idea, that limit, it really bumps up against some fundamental assumptions we make.
Like what?
Well, our standard models, they kind of rely on the universe looking pretty much the same everywhere on the biggest scales. Same laws, same density, roughly, isotropy and homogeneity. But if there's something beyond our horizon pulling on us, this dark flow, that could really shake things up.
Right. So we've got our bubble packed with galaxies. Now the main event, dark flow.
Let's get into it.
The Emergence video explains it as this non-random movement. We're talking hundreds of galaxy clusters.
And these are massive structures, not just little groups.
Exactly. Huge collections of galaxies, all apparently moving together at, around 2 million miles per hour? Incredible speed.
And the kicker is, it's not random directions. They seem to be heading collectively towards one particular patch of sky, somewhere between the constellations Centaurus and Vela.
Which is just not what you'd expect.
Not at all. The universe is expanding. Things should generally be moving apart. This coordinated flow on such a massive scale, it doesn't fit the standard picture.
It's like seeing a whole river suddenly decide to flow uphill. It just feels wrong. And the dark part of dark flow, the NOVA article stressed this. It's not directly about dark matter or dark energy, is it?
No, not in the same way. It's dark because the cause is mysterious. Unknown.
Right. The origin can be something way out there beyond our observable limit, something we just can't detect directly.
Exactly. Or, as the Emergence video even hinted, maybe something even more exotic.
Like another universe.
Like a gravitational pull from another universe entirely. Imagine.
Wow.
The term dark here really just signifies our lack of understanding. Like when we first encountered dark matter effects, we saw the gravity but didn't know the source. Same idea here.
Okay, so what's the actual evidence? The smoking gun, if you like. How did anyone even spot this?
Well, both the video and the Novae article point to the work of Alexander Kashlinsky and his team.
Kashlinsky, right.
And the key tool here is the cosmic microwave background, the CMB.
The Big Bang's afterglow.
Precisely. That faint microwave light filling all of space. Kashlinsky's group used galaxy clusters like giant probes moving through the CMB radiation.
How does that work?
Well, the hot gas inside these massive clusters interacts with the CMB photons passing through them. It scatters the light. And if the cluster is moving relative to the CMB...
changes the light somehow.
Exactly. It causes a tiny shift in the temperature, or the energy, of the CMB photons in the direction of motion versus the opposite direction. It's called the kinematic Synyav-Zeldovich effect, or KSZ effect.
Okay, so it's like a cosmic speedometer using the CMB as the reference point.
It's a good way to put it. It's incredibly subtle, though. Like, really, really hard to measure accurately.
But Kashlinsky's group claimed they did measure it.
They did. And what they reported, as the sources mentioned, was this consistent pattern. Hundreds of clusters, all seeming to move pretty fast, 600 to 1,000 kilometers per second, towards that Centaurus Vela region.
Kilometers per second. That's blistering speed.
It really is. And what made it even more striking, as Space.com pointed out, was that their later work pushed these measurements out to like 2.5 billion light years.
Whoa. So twice as far as their initial studies.
Yeah. Which suggested it wasn't just some local quirk. It seemed to be a genuinely large-scale thing happening deep in the universe.
Okay, that's pretty significant, and obviously significant enough to be discussed at that Royal Society meeting.
Absolutely. The notes from that meeting actually frame dark flow as a potential anomaly within our standard cosmological model.
Which is the lambda CDM model, right? Our best current picture.
Exactly. Lambda for dark energy, CDM for cold dark matter. That's the workhorse model. So calling dark flow an anomaly means it doesn't quite slot neatly into that framework.
It suggests something might be missing or wrong in our understanding.
Potentially, yes, if these observations hold up.
And it's a big but, isn't it?
Yeah.
The Novae article highlights that this hasn't exactly been smooth sailing. There's pushback.
Oh, absolutely. A healthy dose of scientific skepticism. The article specifically mentions Ned Wright, an astronomer at UCLA.
What was his issue?
He raised serious questions about the statistical methods Kashlinsky's team first used. He basically argued that the signal they were seeing might not be a real flow, but maybe subtle errors or biases in how they analyze the CMB data itself.
So maybe it's an artifact of the measurement, not a real physical effect.
That was Wright's concern, yeah. He said, essentially, hang on, let's double-check these numbers. The evidence might not be as robust as claimed.
But Kashlinsky pushed back.
He did. The article mentions he offered a detailed rebuttal, defended the analysis, and crucially, kept looking for more data, better data, to strengthen the case.
Which is how science is supposed to work, I guess. That back and forth.
Exactly right. Extraordinary claims need extraordinary evidence, and that evidence has to survive intense scrutiny.
And the Royal Society meeting mentioned other relevant checks, too.
Yes, things like the Ellis-Baldwin test and looking at the kinematic dipole and the CMB. These are ways scientists try to test if the universe really is isotropic, the same in all directions.
So if there's a massive flow in one direction?
Yep. It might show up as a deviation in those tests, challenging that assumption of uniformity. The meeting also talked about other measurements, these large-scale bulk flow estimates.
What are those?
Basically, measuring the average motion of very large volumes of space. And some of those measurements also seem, well, larger than expected under the standard lambda CDM model. They seem to hint at large regions moving together more coherently than predicted.
Okay, so there are other hints pointing in a similar direction, potentially.
Potentially. It's all part of this picture of tensions within the standard model.
All right, let's play devil's advocate for a second. Let's assume dark flow is real. What are the really profound implications? You mentioned it shakes up fundamental assumptions.
The biggest one is the cosmological principle. That idea we talked about the universe being broadly the same everywhere on large scales, homogeneous and isotropic.
Right.
If you have hundreds of galaxy clusters all streaming in one preferred direction across billions of light years, well, that looks decidedly not isotropic.
It implies there is a special direction in the universe on these huge scales.
Exactly. It would suggest a fundamental large-scale anisotropy, a lack of uniformity that our standard model doesn't account for. The universe might be lumpier or have large-scale structures or influences way beyond what we currently model.
And that leads to some wild speculation, doesn't it? Both Novia and the Emergence video brought up the idea that this pull could be coming from outside.
From beyond our observable horizon, yes. The idea is maybe there's some absolutely colossal concentration of mass out there, a super cluster, or something even stranger.
Something so far away its light hasn't reached us yet, but its gravity still can.
That's the speculation. Gravity reaching across the horizon, pulling on everything within our visible bubble, like feeling a draft under a door without seeing what's causing it.
Or even wilder, the multiverse idea.
That's another possibility they floated. Maybe the gravitational influence of a nearby parallel universe. Something that interacted with our region very, very early on, leaving this large-scale flow as a kind of relic of irregularity, as the Novier article put it.
That just sounds like science fiction.
It borders on it for sure, but when you have anomalies like dark flow potentially challenging your standard model, you have to start considering less standard explanations. Those Royal Society discussions about tensions in cosmology suddenly feel very relevant.
Okay. So besides these exotic, beyond-the-horizon explanations, were there any other ideas floating around? What about that Reddit discussion? That took a different tack entirely, right, about time.
Ah, yes, that was fascinating. Really outside the box. The original poster suggested, what if time itself doesn't flow at the same rate everywhere?
How would it work?
Well, the idea builds on general relativity.
Right.
Gravity warps space-time, and that includes time. So maybe in denser regions of the universe, time flows slightly slower than in the big empty voids. And the poster wondered if this difference in the flow of time, as they called it, could actually account for things like the expansion of the universe or galaxy rotation, or maybe even dark flow without needing dark matter or dark energy.
So, getting rid of dark matter and energy by changing how time works across the universe.
That seemed to be the gist. It's a radical idea, suggesting our perception of these forces might be due to variations in the fabric of space-time itself. Some commenters brought up related concepts like timescape cosmology.
Timescape cosmology?
Yeah, or the lumpy universe model. It explores similar ideas that because the universe isn't perfectly smooth, different regions might experience time slightly differently, affecting how we measure cosmic expansion, for example. It challenges the idea of a single, universal cosmic clock.
That Reddit thread even touched on the laws of physics maybe not being constant everywhere.
It did get very speculative, yes. Definitely pushing boundaries. But it shows how these puzzles make people question everything.
And while those Reddit ideas are maybe on the fringe, you mentioned the Royal Society meeting did highlight established problems, real tensions.
Oh, absolutely. Things scientists are actively working on, like the Hubble tension. We get different values for the universe's expansion rate depending on whether we measure it nearby or using the early universe CMB data. They don't match up.
I've heard about that one.
Then there's the S8 tension about how clumpy matter seems to be today compared to predictions from the early universe. And the ISW puzzle, odd patterns in how the CMB light interacts with large structures as it travels to us.
So dark flow could be another piece in that larger puzzle of things that don't quite fit lambda CDM.
It could be, yes, if it's confirmed. And the R6 paper we looked at adds another piece, finding that peculiar velocities, the extra motions of galaxy clusters on top of the cosmic expansion, are systematically underestimated by our current simple models, especially in really big structures like superclusters.
Which sounds related to large-scale flows.
It certainly points towards motions that aren't fully captured by the standard picture and ties back to those large-scale bulk flow estimates discussed at the Royal Society, meeting observations suggesting regions are moving together in ways that are hard to explain.
What about the Great Attractor? The emergence video mentioned that. Isn't that a known massive thing pulling us?
It is. The Great Attractor is real, a huge concentration of mass that our own local group, including the Milky Way, is definitely being pulled towards.
So maybe that's the source of the dark flow.
Initially, people wondered that, but the dark flow seems to be directed generally towards the Great Attractor's region, yes, but the flow itself seems to extend much, much farther out. The source appears to be beyond the Great Attractor.
So the Great Attractor is just part of the flow, not the ultimate cause.
That seems to be the current thinking. It's like the Great Attractor is also being swept along by this larger, more distant current.
Okay, so lots of questions, lots of debate. Where does the research go from here? What's next?
Well, the Space.com article mentioned the Planck satellite data. That's been foundational.
Our best map of the CMB.
Exactly. But looking forward, upcoming missions are key. Big galaxy surveys like Euclid, which came up at the Royal Society meeting regarding that ISW puzzle.
What will Euclid do?
It's designed to map the distribution and shapes and motions of billions of galaxies over a huge chunk of the sky with incredible precision. That kind of data could potentially give us a much clearer picture of these large-scale flows. Either confirm dark flow definitively or possibly show it was a statistical anomaly after all.
And the James Webb Space Telescope, JWST.
JWST will help too, especially with measuring galaxy distances more accurately using infrared light. That's vital for calculating those peculiar velocities we talked about.
Right.
And there are also upcoming weak lensing surveys. These map how light from distant galaxies gets bent by the gravity of intervening matter, both normal and dark matter.
So they map out the mass distribution.
Exactly. They could potentially reveal the large-scale structures, maybe even structures beyond the horizon that might be responsible for a dark flow if it exists. So better data is really the key.
Okay, so after digging through all of this, the videos, the articles, the meeting notes, the Reddit thread, the paper, what's the big takeaway for you? What sticks?
For me, I think the biggest thing is just how much we don't know for sure. The whole concept of dark flow, whether it turns out to be real or not, it's just such a powerful reminder that our picture of the universe is, well, incomplete.
Yeah.
The very idea that huge chunks of the observable universe might be moving together because of something beyond our sight, it just hints at a cosmos that could be far more interconnected, maybe far weirder than our standard models currently allow for.
It definitely leaves you with a pretty provocative thought, doesn't it?
It does.
If our entire observable universe is being, gently tugged in one direction by something invisible, what does that really say about our little patch of reality and its true extent? Could all these little tensions and anomalies scientists keep finding, the Hubble tension, S8, dark flow, could they be the first signs, the first whispers of a much grander, more complex reality than we've even imagined?
It's humbling, isn't it? And exciting.
Yeah, makes you feel small, but also curious.
Absolutely. And, for anyone listening who's intrigued by this, I'd really encourage them to look deeper into these concepts, understand the observable universe, the cosmological principle.
Dark matter, dark energy.
Exactly. And maybe look up some of those other tensions we mentioned, Hubble tension, S8 tension, the ISW effect, see how they all fit, or maybe don't fit together.
Because it seems like dark flow, real or not, is part of this bigger story of cosmology trying to figure itself out right now.
Precisely. It's a fascinating, ongoing scientific mystery.